We started yet? Okay, here we go. Parametric curves. Here comes the first example. Example number 1. Suppose I have this parametric curve, x equals 20t and y equals negative 5t squared plus 20t. Okay, there's my example. I want to remind you that x and y are the variables, but t is the parameter. We're defining x and y in terms of a third variable, which we call the parameter, hence the name parametric equations or parametric curves. Secondly, suppose this x and y is motion in the x and y direction. So suppose this parametric equation defines the motion of something, moving in the xy plane. And suppose further that I told you that t lay between 0 and 4, okay? Someone tell me, what can you tell me about the velocity only in the x direction? I mean, this particle might be doing whatever crazy stuff in the y direction, but in the x direction, what can you tell me about the velocity?
Constant.
Good. How many people say it's constant? Yeah, good for you guys. Because if I want the velocity only in the x direction, what am I going to have to do to this guy? Get the
Derivative.
If you're thinking derivative?
Oh.
Yeah, if I want the velocity, if this is an expression for the position in the x direction, then the velocity in the x direction would be to take the derivative with respect to time, right? And that would get me the velocity in the x direction, okay? You tell me, what can you tell me about the velocity in the y direction? What's that, Fatima?
It's decelerating.
Okay, cool. She's saying it decelerates. Is everybody in their heads taking the derivative of that? Okay, so let's go for it. Let's take the derivative of y with respect to t. So I get negative 10t plus 20. Good. She's right. It's well, let's see about this. When t is equal to 0, is the velocity positive or negative? Good. Tell me, at what point is the velocity equal to 0? Good. So what happens? Describe for me what's happening at 2 seconds. If this is telling me its motion in the x direction, and this is telling me the motion in the y direction, and initially it's going up, what happens at 2 seconds? Yeah, Daniel? Yeah, it turns around. It's momentarily at rest. Correct? Yes. Yeah, it's at its relative maximum, it turns out. Okay, good. I just want you to be thinking in terms of parametric. Have your brains go to parametric land. And of course, we can talk about acceleration. What's the acceleration in the x direction? 0, which means the velocity is never changing in the x direction. But the acceleration in the y direction, a sub y, which is going to be the second derivative of y with respect to t, is just negative 10. So why would Fatima say, oh, it's decelerating? Why would she refer to the motion in the y direction as being deceleration? Yes?
Because it's concave down.
Okay, because it's concave down. Beautiful. What else? I mean, what do you notice about that number? Yeah, it's negative. But actually, it's not decelerating over this entire time. Remember, this particle is moving up, then it reaches some maximum point, then it's moving down, okay? And this happens at t equals 2. So what's the only time that this particle is actually in the y direction decelerating? Yeah, in the first 2 seconds. In the first 2 seconds it's decelerating because the acceleration is in the opposite direction of the velocity. But after it reaches here, now it's accelerating, it's going faster and faster in the y direction, okay? This is all intro. This is just to kind of remind you about parametric equations, to kind of access some of your knowledge about physics, those of you who've had physics, and it's pretty cool. But now we're going to talk about something actually different from everything I've talked about. Sometimes it's really useful to know the direction in which you're traveling at a particular point in time. For example, if I'm right here at t equal 1 sec, oh, that was bad. Here, just a second. Here. If if I happen to be about right there, because at t equal 1 second, I mean, how much progress should I have made? If this is 2 seconds, where should my little orange dot be at t equal 1 second? Yeah, about halfway. Because my progress in the x direction is uniform, it's constant. So I drew it wrong the first time. Yeah, it should be about right there. T equal 1. Okay. Sometimes it's useful to know the direction in which I'm traveling at a particular point in time. Okay. I would like to know at 1 second, hey, I'm traveling in that direction. So if I want to know the direction I'm traveling, or I want to know the line on which I'm traveling at that point in time, as you can see visually, what am I going to have to get?
Tangent.
Yeah, the derivative, the tangent line. I need to get the slope of the tangent. And none of this stuff was getting the slope of the tangent. This was just considering, it was separating motion in the x and y directions, which are completely independent of each other. But now, for the rest of the period, we're going to be dealing with, okay, slope of the tangent of parametric equation, concavity of the parametric curve, and we're not going to be splitting the x and y directions. We're going to be treating this just like all the curves we've treated all year. But I just want to let you know that the usefulness of parametric curves is this ability to separate the x and y directions. But we're not going to do any of that today, no siree. So let's go ahead, let's get dy dx of parametric. That's the first thing we're going to do. That's that guy right there. Okay, here it is. I'm not going to beat around the bush. You know what dy dx is the same as? Dy dt over dx dt. Are you okay? I just divide the dy by dt, divide the dx by dt. Actually, this is an example of the chain rule, but I'm not going to do it that way. I'd rather have you just remember it this way. And so if I want to get an equation for the slope of the tangent, all I have to do is put dy dt in the numerator, negative 10t plus 20, and put dx dt, which is 20, in the denominator. That's it. That's my equation for dy dx. This ends up being 1/2 t plus 1. So if someone asked me, get slope of the tangent at t equal 1, that would be easy. Dy dx evaluated at t equal 1 would equal 1/2. So the slope of that tangent is 1/2. Is that okay with you guys? Okay, then let me see if I can have you guys do a problem like this. Here we go. You see, here, for x equals rad t, for x equals rad t, and y equals t minus 1, A, get dy dx, and then B, get slope of the tangent at t equal 4 seconds. Good luck. How many people here got 2 radical t? Yay, yay for all of you. Goody. And let's get the slope of the tangent at t equal 4. dy dx evaluated at t equal 4 is going to equal t times radical 4, which is 4. Yay. How many people got 4? Okay, good. It's that simple. Great. Let's go ahead and do more. Let's do more of this slope of the tangent stuff. Sometimes it becomes important to us to find where the slope of the tangent is 0, which means it's going to be like where your y coordinate turns around. And sometimes it's important to find where the slope of the tangent is infinity, which is going to be quite often where your x turns around. Sometimes it won't, but sometimes it will. The same with the y. If the slope of the tangent is 0, sometimes it turns around, sometimes it doesn't. But still, it's important to find those 2 types of tangents, horizontal and vertical tangents. So that's what I'm going to do now. If you follow along on my little whiteboard. Let me see. Find points of vertical and horizontal tangency. Okay. Here it comes. X equals 2 plus 3 cosine of t, and y equals 1 plus 2 sine t. Please write that down. Vertical and horizontal tangency. Well, in order to do that, I think it's pretty obvious I'm going to have to find dy dx, which means I have to find dy dt over dx dt. Alrighty. So dy dt is 2 cosine t, and dx dt is negative 3 sine t. So here's my question to you. How am I going to find points of horizontal tangency? Well, if I have a horizontal tangent, what is dy dx equal to? 0. How am I going to make that fraction equal to 0? What should I do?
Set it equal to 0.
Okay, great. When I have a fraction, if I want the value of a fraction to be 0, what part of the fraction? Yes, Fatima?
The numerator should be equal to 0.
Yeah, thank you. You guys okay with that? I need the numerator to be 0. That's the only way I'm going to get this fraction to have a value of 0, is if the numerator equals 0. So for a horizontal tangent, set, the numerator equal to 0, which is another way of saying set dy dt equal to 0. So let's go for it. 2 cosine t equals 0. Let's have t. Do you mind if we have t go from 0 to 2 pi? We'll have t go from 0 to 2 pi. So the values of t that make cosine t equal to 0 are going to be t equals what? Pi over 2, 3 pi over 2? Great. Which means since I want the points, I need x and y. I'm going to have to find what x and y are. So when t is pi over 2, that makes x 2, and that makes y 3. And when t is equal to 3 pi over 2, that makes x 3 pi over 2. That's still 0, so it's 2. And then 3 pi over 2 is negative 1, so that's negative 1. Okay? Great. Someone tell me, how am I going to find the points of vertical tangency? Yes, Chris? Absolutely. Set the denominator equal to 0. For vertical tangents, set the denominator equal to 0. That is set dx dt equal to 0. I'd like everyone to please do that right now and find me the points of vertical tangency. Hopefully everyone here is applying -3 sine t equals 0. It's going to be the same as that guy. So, you guys getting the point -1, 1 and 5, 1? Okay, now we could have observed this just by graphing the stupid thing, right? Do you remember how we graph parametric equations? What do? Like if I don't have a graphic calculator. I'm going to make a chart. How many columns is my chart going to have?
3.
Yeah, 3-column chart. So sure, if you want, you make a chart, a 3-column chart. Me personally, I'm going to do the 3-column chart in my head. So when t is equal to 0, x is equal to 5, and y is equal to 1. So I'm going to be right there, 5, 1. Okay, and this is going to be when t is equal to 0. When t is equal to pi over 2, I'm going to be at 2, 3. So here's 2, 3. So I'm going to be like right there. And then this is when t is equal to pi over 2. When t is equal to pi, I'm going to be at -1, 1. So I'm going to be right there. T equals pi. I think I kind of made this guy bad. Here. 1, 2, 3, 4, 5, whatever. So boop. And then when t is equal to 3 pi over 2, where am I? Right there. Then it's 2, -1. 2, -1. So you know, I've got something that looks like this. It's an ellipse, okay? Remember, when you make a parametric graph, it's going to have orientation. So put the little arrows to show which way it's going. And then it's pretty obvious just by looking at the graph that I'm going to have horizontal tangents at 2, 3 and at 2, -1. And I'm going to have vertical tangents at 5, 1 and -1, 1. Okay, but this is a convenient way to find those points of vertical and horizontal tangents. And just remember who gets to be set to 0 for horizontal tangents, set the numerator to 0. For vertical tangents, set the denominator to 0. Let me ask you one more question. What if there ends up being a value that makes both the numerator and the denominator 0? That is, what if there was some weird value such that, you know, when you plug them in, okay, you plug in some value, some special value, and you end up with 0 over 0, what are you going to have to do to decide if it's a vertical or horizontal tangent? Who said that? Zach, thank you very much. Whenever you see 0 over 0, remember, it makes you very happy. You're going to have to do L'Hopital's rule. Yeah, if you want to know definitively, is this a vertical tangent, is it a horizontal tangent, is it neither of the above, you're going to have to do L'Hopital's rule. But on this particular problem, that didn't come up. Okay, alrighty. Well, hey, it's time to do the second derivative. Thank you for your patience. By the way, this is chapter 10. We're starting chapter 10. Let's get second derivative of parametric. Do you remember how the first derivative of parametric was dy dt over dx dt? Okay? Question? Well, most people think, okay, to get the second derivative, I'm just going to have the second derivative of y over the second derivative of x. Most people would think that. But here's the weird thing. What if I had that last example I had? This was example number 1, where x equaled 20t and y equaled negative 5t squared. Was it negative 5t squared? I forget now. 5t squared plus 20t. Okay. Yeah, that was it. Tell me, if I just put the second derivative in the numerator and the second derivative of x in the denominator, what would I end up with? What's that? Yeah, I'd end up with undefined, because the second derivative of x is 0. The acceleration in the x direction is 0. I would end up with an undefined second derivative, but we know it's not undefined. Tell me, what would I expect my second derivative to be? Yeah, thank you, some negative number. Good job, Zach. Yeah, it's just some negative number. So it obviously can't be the second derivative of y over the second derivative of x. That can't be it. What is it? I'll show you. Here we go. Ready? The derivative with respect to x of dy dx, okay, is the derivative of dy dx with respect to x. You got a dy dx. Why did I put a t there? Are you okay that all I did was just put this in the numerator? The second derivative, the derivative of the first derivative, is this. And now I'm going to do that divide by dt thing. I'm going to say that this is the same as the derivative of dy dx with respect to t over dx dt. And that's my second derivative. That's how I get my concavity. I take the derivative of this guy, put it in the numerator, and in the denominator just dx dt goes there. Let me show you how that plays out. For this example, x, here, I've already got it there. For this example, dy dx is equal to dy dt over dx dt, which ended up being negative 10t plus 20 over 20, which ended up being negative 1/2 t plus 1, okay? The second derivative is going to be the derivative of that guy, negative 1/2 t plus 1, with respect to t over dx dt. I take the derivative of that guy with respect to t and put that over dx dt. So the derivative of this guy with respect to t is negative 1/2. dx dt, we already found it was 20. So I get, just as Zach predicted, some negative number. And there it is, it's negative 1 over 40. That's the concavity. That's the second derivative. It's always negative because it's always concave down. You guys okay with this? Just whatever you got for your first derivative, take the derivative of it and then put that over dx dt. Don't be doing second derivative over second derivative. Okay, here's one for you guys to do. Okay, x equals t to the third minus 3t plus 1, y equals 2t plus 1. If you were to graph this curve, the graph would look something like this. Okay? And so here's what I want you to find. Number 1, find the second derivative, that is an expression, you know, for the second derivative, and then B, find the inflection points. That is, you know, find this guy. You're gonna have an inflection point right there. Go ahead and find it. I think, no, is that, no, there's more than that. I'm looking at it sideways. Oh, how stupid of me. What kind of concavity does it look like it has here? Up. And then what kind of concavity does it have here? Down. And then here, up. So you're gonna get a lot of inflection points. You've got an inflection point there. This is concave down. This is concave up, so you'll have an inflection point here. And then this is concave down, so you should have an inflection point there. You should end up with 3 inflection points, you know? Yeah, freaky. So anyway, good luck. Then I'll teach you about arc length. Amber. Sarah. Yes? Sure. Does anyone have any trouble getting started on this? Maybe I'll factor out the 3. Yeah, I'm going to factor out the 3. My goodness. My God. Right? Yes.
I'm not sure that one divided by the over dt, but that one divided by dx over dt.
Wait, here?
Oh, never mind.
Okay. And I gotta tell you guys, I found it really convenient to factor the 3 out of the denominator, but if you didn't, that's okay. No, I did it by factoring the 3 out of the denominator, so I was only dealing with t squared minus 1 instead of 3t squared minus 3. But did anyone get something that looks like this? Okay, yay, Lauren. Okay, one way to check, you tell me, oh, well, let me just stop for a second. Does anyone need to catch up? Okay, did anyone get, instead of what I got, did you keep the 3 with it all? So you ended up with, what is that, -2 over 3t squared minus 3 squared times 6t, okay, over 3t squared minus 3, so you end up with -12t over 3t squared minus 3 to the 3rd power. Did anyone get, is that correct? Did anyone get that? Okay, good. Because I think it's the same, right? If I factor the 20, if I factor the 27 out, then this becomes 4 and that becomes 9. Yeah. So if you got that, you're fine too. Go ahead.
Why did you, why did you keep the t squared minus 1 and erase the -2 and put it down with the other one? Like so when you factored out the denominator there?
Which one are you talking about, here?
Yeah.
Or here? Here?
Yeah, there.
Okay, here. Yeah, I factored the 3 out, so I had -2/3 times t squared minus 3 to the -1 power. You see, this guy here is the same as 2/3 times t squared minus 1 to the -1 power. And then when I took the derivative of this, I end up with -2/3 times t squared minus 1 to the -2 power. Then I have to multiply by the derivative of t squared, which is 2t.
Yeah, and so
Yes.
when I brought it back down, it was just 2 over 3 times t squared minus 1. I got a different, and so then that way there was like 2 denominators technically.
Oh,
There's
okay,
3 level
so
fractions.
you ended up with something like this, like -2 times 2t over 3t squared minus 3 times t squared minus 1 to the 2nd? Do you have something that looked like that? Maybe?
No, it's weird, so I ended up like.
Because they don't, I mean, if I've got t squared minus 1 to the -2 in the numerator and t squared minus 1 to the +1 in the denominator, that makes a grand total of 3 of them in the denominator.
Yeah, but when you divide by that, don't you put the 3 times, because I factored out the 3 in both of them.
Okay.
So I ended up with, so my fraction looks like 2 times 2t over 3 times 3t squared minus 1 over 3t squared minus 1. Or the second one.
It shouldn't be over it. I mean, if you have -2 power in the numerator, that's +2 power in the denominator, there's no getting around that. It's not going to be a denominator of the denominator.
But don't you have the fraction there?
Yeah, I mean, I've got a fraction here, and I have a negative exponential in the numerator, which is the same as a positive exponential in the denominator. I mean, don't think of it any other way, you know? I mean, if you want to turn this into a fraction, great, but if you turned it into a fraction, that denominator means that it goes in the denominator here. You know, I mean, if I have 1/2 over 5, that's the same as 1/10. You know, because the 2 just goes with the 5.
Oh, okay.
Well, anyway, whether you got this answer or that answer, you tell me. What are the possible inflection points? Say again.
0, 1.
Yeah, 0, 1, and -1. Remember, your possible inflection points. Make the second derivative 0 or make the second derivative undefined. So yeah, you got possible inflection points at t equals 0, -1, and 1. And then the only way to test for sure if those are inflection points, you're going to have to do check for concavity. And let me do that over here really quick. Then I got to teach you arc length, and we may not get to the review. Well, we'll do that Monday. It'll be fine. Plus, you'll have the whole weekend to have questions. But here, I mean, now, since I have possible inflection points, we're going to check for concavity. Alrighty, which means I'm going to go from -infinity to -1. I'm going to go from -1 to 0, and I'll go from 0 to 1, and then 1 to infinity. These are the intervals of t. and then I'm going to look at the sign of, y double prime, which is the sign of the second derivative. When I stick in a big negative number here, I'm going to get a positive on top, and I'm going to get a positive on the bottom, so that's going to be positive. If I stick in negative a half, I get a positive on top, but I'll get a negative down here. If I stick in positive a half, I get a negative on top and a negative down here, which makes positive. And then if I plug in a million billion, I get a negative on top and a positive on the bottom. So yeah, those are indeed my inflection points. I have inflection points at t equal -1, 0, and 1, which means I can actually find those three coordinates, boom, boom, and boom. Stick in t equal -1, and I got -1 minus -3, which is 2, plus 1, which is 3. Stick in -1, I got -2 plus 1, which is -1. Plug in 0, and I got 1, 1. And then plug in 1, and I got 1 minus 3 is -2 plus 1, which is -1. And plug in 1, and I got 3. Yeah, so there it is. Those are my 3 inflection points. So hey, be prepared to do a problem like this. Be prepared to get a second derivative, and then, find your inflection points and check for concavity. Any question or problem on this process? You'll have to be really careful about your algebra, though. You guys good on this? Yeah, just remember, it's whatever you find for dy dx, it's the derivative of that in the numerator. Dx dt goes in the denominator. Okay. Well, hey, last but not least, arc length of parametric. We'll have to do this in 5 minutes. But it's really easy. It's just just plug into the formula. Here we go. Arc length for parametric. There's my parametric equation, or my parametric graph. Okay, let's say it looks something like that. Okay, great. And I want to get the arc length from there to there. Okay? The easiest way to get the arc length is to just make a bunch of straight lines, essentially kind of doing the trapezoid rule thing, but not adding up, not adding up areas. Okay, so you're going to add up just a bunch of straight lines, and each line is going to have a delta x associated with it and a delta y. So I'll have delta x1 and delta, oh, please don't write this down, just watch and enjoy. So here, and then this guy is going to be delta x2 and delta y2, and this guy will be delta x3 and delta y3, and so on. You just add up a whole bunch of these hypotenuses, which, by the way, if this is delta x and that's delta y, then the hypotenuse is going to be the square root of delta x squared plus delta y squared, right? So what I'm really adding up is a bunch of hypotenuses. I'm adding up a bunch of square root of delta x squared plus delta y squared. So I get to say this. Arc length, which we call S, ends up being the sum of all of the delta x squareds plus delta y squareds. That's it. We're just adding them up. But guess what happens next? I'm going to divide these guys by delta t squared and put out a delta t squared. I'll show you what I mean. Okay? This is now delta x over delta t squared plus delta y over delta t squared times delta t squared. Are you okay that what I have here is mathematically the same as what I have there? And like I said, just look at it. See if you believe me. You believe I'm not a liar. And by the way, this is an infinite sum as n goes from 1 to infinity, and so, or I guess I'll call it, x sub n, y sub n, x sub n, y sub n as n goes from 1 to infinity. All right, well, this is the same as the sum as n goes from 1 to infinity of the square root of delta x over delta t squared plus delta y over delta t squared times delta t. And then through the magic of Leibniz notation, I'm going to rewrite this as an integral. And this will be the integral from the initial time to the final time of the square root of dx dt squared plus dy dt squared dt. And that's it. That's, there it is. There's the arc length formula for parametric. And you will definitely only be doing this on your graphing calculator. I'm not going to ask you to actually do it in real life. Okay? So let me just scribble an example on here and then send you on your way. And hope that that's good enough. Here, suppose I had x equals t to the third, and I had y equals 3/2 t squared, alrighty? And I want the arc length from 0 to rad 3. Here's all you have to do. The arc length is going to be the integral from 0 to rad 3 of the square root of that guy, the derivative of that guy squared, plus the derivative of that guy squared, dt. And then you just plug it in your calculator and you got a winner. And it ends up equaling 7. So is that okay with you guys with arc length? Remember, it's the initial t to the final t. And then, yeah, the derivative of the x guy squared, the derivative of the y guy squared. Cool. All right, good luck, you guys. And I'll say bye-bye.